So today we will continue sort of exploring mainly observational properties of magnetic fields for different types of stars. And we decided that it's too much for you to have 2 hours straight, so I will make 10 minutes break at 9:55, say. Okay? So remind me if I forget about the break. So since you had lots of things happening after my previous lecture, and you heard other talks, and we had nice excursion up to today, I think it's worthwhile to remind you a little bit where we are and what we're talking about. So first of all, I have introduced basic principles of diagnosing stellar magnetic field. I introduced equation of polarized radiative transfer, which is really our bread and butter in this business. And I showed how this equation can be simplified in various cases, cases like Milne-Eddington atmosphere, cases like weak field and weak line approximation. And I introduced a number of what is known as magnetic observables, so quantities which are derived from stellar observations and which tell something about magnetic field. So in particular, I was talking about these things from the simplest magnetic observable, and the one which is probably relies on the least number of approximations is measuring simply the separation between pi and sigma components, or sigma components in the spectral lines resolved by the Zeeman effect. So in that measurement, we are deriving what is known as mean field modulus. So that's the disk averaged modulus, absolute value of the magnetic field. However, this kind of measurement really requires very strong fields and very slow stellar rotation. Just to give you an order of magnitude, there is this rule of thumb that magnetic field in kilogauss have to be comparable to stellar projected stellar rotational velocity in order to see the Zeeman splitting. And also, you should take into account the intrinsic line width. So line width of stars, if they would not have any rotation, is around 2-3 kilometers per second. So it means that we can see Zeeman splitting only for stars which have almost no rotation and fields above several kilogauss. Then I talked a little bit about measuring magnetic field at low spectral resolution using so-called photopolarimetric methods. There we can, for instance, have narrowband filters tuned for the blue and red wing of some spectral line, like broad hydrogen lines in early type stars. And we can derive what is known as mean longitudinal field. That is the disk averaged line of sight projection of magnetic field. There is also another technique related to low resolution photopolarimetric methods, and that is simply to measure Q and U Stokes parameters over broad wavelength regions in Johnson BV, for instance, filters. And that is sensitive to so-called broadband linear polarization, which arises due to differential intensification of pi and sigma components. Then going towards in the direction of increase of spectral resolution and spectropolarimetric observations, there is a number of things one can do with medium and low resolution spectropolarimetry. And in particular, I mentioned that there is this moment technique, which relates moments of Stokes profiles to the moments of magnetic field integrated over the star. And in practice, these 3 moments are most often used. So Stokes V first moment of Stokes V gives again mean longitudinal field. And you could say that this moment, first moment, characterizes the asymmetric part of the Stokes V profile. Maybe it's worthwhile to remind you what the equation was for so for the longitudinal field, what we have to do is to integrate Stokes V profile multiplied by this difference in wavelength, which is calculated relative to center of gravity of Stokes I profile. And this is normalized to the equivalent width of spectral line. So you can see that this is basically sensitive to asymmetric part of Stokes V, because this part, this term, has different signs on different sides of the spectral line. And then we can also formulate a second moment of Stokes V profile, which would have exactly the same formula, except we have square here. And that observable characterizes symmetric part of the Stokes V profile, and it can be connected to the integral of line of sight component multiplied by the distance from the center meridian of the star to a certain point on the stellar surface. So this is called crossover or asymmetry of longitudinal field. And then one can also look at signatures of Zeeman broadening and try to relate width of Stokes I line, so simple unpolarized spectrum. Different lines have different magnetic sensitivity, and therefore they are broadened in different way by magnetic field. And that can be formalized in terms of this observable, so-called quadratic magnetic field, which is actually a sum of average of b squared plus average of bz squared. And then the really ultimate method of looking at exploring stellar magnetic fields and exploring in particular geometries of stellar magnetic fields is observing stars, magnetic stars, at very high spectroscopic resolution and recording full line profile information in Stokes parameters. So studying spectral line profiles with enough resolution to fully see what is the structure of Q, U, and V signals. And this kind of observations can be interpreted, for instance, using Zeeman Doppler imaging, the inversion technique which reconstructs two-dimensional maps of stellar magnetic fields from time series observations of polarization in spectral lines. Then I started to go through different types of stars, and that's where we are. So I discussed solar type stars and started talking about intermediate mass stars. And it's useful maybe to keep in mind the basic properties of each of these types. So I again very briefly say about this. So solar type stars I define in this way. So it's really between M and F spectral types, this range of masses in the theoretical HR diagram. And the key properties of magnetic fields in these stars are summarized here. We can say that all stars of this type have magnetic field. This magnetic field is generated by a dynamo mechanism, so something that constantly regenerates the field. The efficiency of this dynamo mechanism is dependent on the stellar rotation. So the faster the star rotates, the more magnetic field it generates. So this is why the most magnetically active solar type stars are those which have young age, so they still didn't manage to get rid of their initial rotation, and also stars which happen to be in binary systems where there is tidal locking between two components and they're forced to rotate rapidly. Magnetic fields generated by dynamo mechanisms is typically rather weak, so we're talking about fields below kilogauss typically, maybe a few hundred gauss. The field is complex, the field is evolving fairly rapidly, and the field shows cyclic behavior in some stars, and through many decades of studies of magnetic activity of solar type stars, there was this reliance on indirect activity indicators, proxies like emission in HNK, like X-ray emission. But nowadays we shift in the direction of really studying magnetic field topologies with Stokes parameter observations, with Stokes V in particular. The origin of dynamo, where exactly it operates, how it operates, is currently a hot topic. It's not known, but presumably the two most popular directions of thinking about dynamo is that one possibility is to have dynamo associated with places in the stellar interior where we have the maximum shear. And for the Sun, this place is located at the base of the convection zone, which is called tachocline. So we're talking about tachocline dynamo. An alternative would be to have dynamo distributed all over the stellar convection zone. And this is sometimes called turbulent dynamo. What is the relative contribution of each type of dynamo to individual types of late type stars is uncertain at the moment. I think it's even uncertain even for the Sun. So there are simulations which are able to reproduce certain properties of solar magnetic field without any tachocline dynamo, using only turbulent convection. Now, then I started with intermediate mass stars, and they are defined in this way. So stars more massive than about 1.5 solar masses and below 8 solar masses. And this region in the Hertzsprung-Russell diagram is maybe the most important characteristic of the surfaces of these stars, is that these stars are very quiet, in the sense that they don't have powerful surface convection zones and they don't have stellar winds, because for stars more massive than this, wind is really strong. Observational properties of these stars in terms of the magnetic fields are very, very different in comparison to solar type stars. So this is why I think it's worthwhile to remind you of these two groups of stars and compare them. So unlike late type stars, where we more or less sure that every star has magnetic field to some extent, these stars have really a certain subgroup which is observably magnetic. Only about 10% of these stars are observably magnetic. And they have magnetic fields which are quite strong. So between roughly half a kilogauss, and the record holder at the moment, so-called Babcock star, is this 34 kilogauss magnetic field. Magnetic fields in these stars have global organization, meaning that if we, for instance, observe longitudinal magnetic field, usually what we get is a simple sinusoidal curve, indicating that, well, presumably, its magnetic field is roughly dipolar. These stars, A-type stars, B-type stars with magnetic fields, are also distinguished by their very slow rotation in comparison to what is normal for A-type stars. Normal for A-type stars is having rotation periods of just a few days, while these guys, magnetic stars, some of them may have rotation periods of several decades, and the longest rotation periods are believed to be of the order of 100 years. This is presumably related somehow to the presence of strong magnetic field. This magnetic field might help during early stages of stellar evolution, help to get rid of angular momentum. So it slows down stellar rotation. Similarly to how spots of low temperature represent indication of the presence of magnetic field in cool stars, in hot stars, in intermediate mass stars to be precise, there are also spots, but spots of chemical elements. And also the gradients of chemical composition exist not only horizontally in the form of spots, but also vertically in the atmosphere. And just to give you an impression what kind of how these chemical anomalies show up in the spectra of these stars, I here compare two spectra of the top blue spectrum is actually Procyon, so a normal F-type star. And the bottom spectrum is actually a cool AP star with a temperature very close to Procyon, 6,500. But you can see that it looks completely crazy with lots and lots of absorption lines. And then if you try to identify these lines, try to associate these absorption features with chemical elements, it turns out that this star is actually iron poor. And all lines that you see here are produced by heavy elements, by rare earth elements. So this, in particular, this star, well, it's the most extreme star. I'm really trying to impress you here. Some people call it the most extreme, most peculiar star in the sky. And at some point there was even a suggestion that it's some civilization dumping their waste on their star. But all these lines are due to things like europium, neodymium, praseodymium, lanthanum, barium, so heavy elements. The reason why these stars have such anomalous spectra and non-solar chemistry at the surfaces is believed to be an effect called atomic diffusion. So basically what we have is, imagine some atom located somewhere in the interior of the star or in its atmosphere, and there are two basic forces which act on this atom. So there is gravitational pull downwards, and there is a radiative force pushing it upwards. And different elements have different spectra. So some elements have lots of spectral lines, other elements have very few spectral lines. So this radiative force is quite different. And also radiative force can change a lot if we ionize elements. So for instance, singly ionized might be supported by the radiation, and doubly ionized might not be supported. So the balance between these two forces explains why these stars have anomalous chemistry on the surface. So basically some elements sink out of the atmosphere, other elements accumulate in the atmosphere. But it is believed that in fact these stars on average, their bulk chemical composition is normal, is solar. And the reason why these particular stars are showing this chemical diffusion effects to such a large extent is precisely because they have quiet atmospheres. They don't have mixing in the surface layers. They don't have winds. So there are no mixing processes destroying this layering of chemical elements produced by atomic diffusion. The overall picture of magnetic fields of these stars is this one. So basically it's so-called oblique rotator model. Magnetic field is not intrinsically changing with time. It is frozen in the stellar atmosphere, and to a first approximation, magnetic field is for 90% of the stars maybe can be represented with oblique dipole. And as this dipole rotates, we see different projection of the magnetic field, and we see different disk average field strength and different field orientation, and the Stokes parameters change. And then in addition to that, there are chemical spots which modulate spectral line profiles. And this time series, which I'm demonstrating here below, can be used to reconstruct two-dimensional maps of stellar surfaces using Doppler imaging. I mentioned that there are analytical formulas relating magnetic observables, such as the mean longitudinal magnetic field and mean field modulus, with the parameters of dipolar field. So for these stars, one can make a very simple models by just making this fits with these formulas to observations of these observables. And in particular, one can deduce the field strength, dipolar field strength, inclination of the dipole relative to the rotation axis of the star, and even the inclination of the stellar rotation axis. So how much rotation, what angle rotation axis makes to the line of sight. And actually that contributes to some general understanding of stellar populations. That's the way, for instance, to address the questions like, are stellar rotation axes distributed randomly? Or is there some preferred direction, maybe in the solar vicinity or maybe in some stellar association of rotation axis of the star? So these stars are used for this purpose, for instance. And these are examples of fits of dipolar field done for this intermediate mass magnetic stars. So in this case, you see just longitudinal field, and this sinusoidal fits give you dipolar field parameters. Now, it turned out that when we have magnetic observable, if our magnetic observations are limited only to deriving longitudinal field, then things are relatively simple. We can we see more or less a sinusoidal curve, and we can derive these dipolar field parameters. But as soon as we introduce other magnetic observables, like we're trying to interpret together longitudinal field and field modulus, or if we are considering these two other observables, crossover and quadratic field, so 4 observables in total, then things become more complicated. It becomes more difficult to reproduce them with simple dipolar fields. And so over the years, mostly in 80s, 90s, people have introduced various deviations from dipolar fields to model these stars. And it really depends whom you ask. There are different people using different models. So some use offset dipole, so the axis of the dipole is displaced from the center of the star, either along the axis of dipole itself, then it is characterized by just one additional parameter, or displaced by some vector, so then it's characterized by 3 vector components. And such offset dipole is illustrated here, for instance, so it's kind of asymmetric, distorted. Then another popular way of parameterizing this field is to introduce, in addition to dipole, introduce axisymmetric quadrupole and octupole fields, and such fields are illustrated here. So a quadrupole has sort of axisymmetric quadrupole have the same sign of field on 2 poles, and then different sign here in the middle, and octupole is even more complex. So what people would do, they would try to reproduce magnetic observables by combining dipole, quadrupole, and octupole with different weights. And, well, there are other possibilities, like using non-axisymmetric quadrupole and even putting some individual magnetic charges, of course, pairs of charges on the stellar surface. And then most recent studies that tried to systematically interpret magnetic observations of intermediate mass stars, they used this more sophisticated low-order multipolar models. And these multipolar models then give the same parameters, well, dipolar field, inclination, obliquity of magnetic field, but in addition to dipole field, they also are able to find quadrupole field and so on. So these are typical examples of how these feeds to magnetic observables look like. So in this case, you see a longitudinal field. This is this crossover asymmetry of Stokes V profile, and then this is field modulus, and this is the quadratic field. And actually, these two examples of two studies, they show the fit to the same star. It's one of the brightest AP stars, Beta Corona Borealis. And in this case, they model the same for the same four magnetic observables, and then in addition, they also look at this broadband linear polarization. Well, this is how it looks. So for some observables, things are similarly good, so good fit. For other observables, you know, there is systematic offsets and deviations. And it is not so easy to say whether these deviations indicate a more complicated field or maybe some mistakes in the fitting. So this is what we have. But there have been some interesting results obtained using this systematic application of multipolar models to intermediate mass stars. So one of the results that has made the greatest impression on theory in particular and on people working in this field is the finding that there exists a correlation between rotation periods and magnetic obliquity. So this angle that dipole makes with the axis of rotation, it tends to be small for slowly rotating stars. So this is illustrated, for instance, here. These are cumulative distribution functions of this parameter, which is just the ratio of the minimum and maximum longitudinal field. And so if this parameter is negative, it means that we are seeing different signs of longitudinal field, which usually happens when the inclination is large. So we see a field like that. So we see both poles, field changes sign. If this parameter is here, if it's sort of has positive sign, it means that minimum and maximum of longitudinal field curve have the same sign, so we are looking at the same pole, and this typically happens when obliquity, this beta angle, is small. And so there tends to be sort of this critical rotation period of about 25 days. So stars which have rotation periods below that have large beta angles, and stars with rotation periods above that tend to have smaller beta angles. And that's another study, and basically it shows similar trends. So here they just plot beta as a function of rotation period. And you see that only for stars with relatively small rotation periods, 10 days or so, 20 days, they have this cloud of large beta angles. And for, yes? Well, in this case, this of course only works for dipole, but usually contributions of quadrupole are small. So for the majority of stars, it's still maybe 70% dipole, and then quadrupole is introduced to fit some smaller features of these magnetic observable curves. And, well, actually in this particular study, they have used parameterization where dipole and quadrupole were aligned. So beta angle is describing both quadrupole and octupoles. In that case, it makes sense. So that is something that theoreticians have looked into, and there were some ideas why this could be. There's some precession of, maybe there is some precession of magnetic axis, and with stellar age, as the star slows down, they tend to get aligned fields, but it's not really understood. Now, the disadvantage of this simple multipolar models applied to intermediate mass stars is that really they have to be understood not literally, in the sense that we are not really deriving the surface map of magnetic field, but rather we are deriving statistical distribution of field modulus, line of sight component, and so on. And this becomes rather clear if one tries to apply these different magnetic parameterizations to the same observational data set and compare resulting distributions of magnetic field. This is what I did in some study. So I took these different parameterizations. So one is dipole, quadrupole, octopole, which are aligned. Another is non-aligned dipole and quadrupole. So something that is used by different authors. And then I tried to fit longitudinal field, quadratic field, and this asymmetry of longitudinal field crossover for some star. And I also had 1 point for the field modulus measurement, well, which is, it's a quite strongly magnetic star, so it has the field reaching 30 kilogauss. And, well, as you can see, different models, so different curves here correspond to different parameterizations. They sort of fit more or less magnetic observables. Maybe here for the field modulus curve you can claim that one is better than the other, but I would not go that far, having only 1 point. But if one plots the resulting magnetic maps, and this is plotted for this 3 best fitting models. So this is the axisymmetric, collinear, dipole, quadrupole, octopole, and these correspond to other parameterizations. So the top shows, in each pair of rows, the top shows the distribution of the field strength, field modulus, and this is the vector map of magnetic field. So you can see that I'm getting reasonable fit here, but the actual underlying distributions are looking quite different. So these distributions have the same statistical properties in the sense that at certain rotation phases they give the same line of sight component and similar quadratic field and so on, but the actual maps are different. And furthermore, if we try to verify, to try to check this magnetic models, multipolar magnetic models, by comparing directly their predictions with observed Stokes parameter profiles, we find very often that they don't fit observations. And so this is an example of actually the first study that tried to do this. So they have these curves of magnetic observables, in this case longitudinal field, field modulus, and this broadband linear polarization. They fit combination of dipole and octopole to these observations, and you can see, well, they get almost perfect fits. But when they take the actual spectra in 4 Stokes parameters of that particular star, then the situation looks like that. So this is Stokes I, Q, U, and V. And the observations are shown here with symbols, small round circles. And then prediction of the model which fits observables is the thick blue line. And red line is prediction of some other model that they took from the literature. So you can see that, well, there is reasonable fit to Stokes I. So, you know, at some phases, the line is narrow. At other phases, magnetic field modulus is larger, so the line is partially split and broadened by magnetic field. You can say that there is some agreement between Stokes V profile and predictions of the models. But, you know, the predictions for Q and U look very, very bad. So the models predict higher amplitude in both Stokes parameters compared to observations. So again, this points to the fact that such simple models have to be understood not literally, but only in statistical sense. So what we are trying to do now, more systematically for different types of stars, is really to explore the information content of full 4 Stokes parameter observations of these intermediate mass magnetic stars. And here we are in a privileged position compared to all other types of magnetic stars, because that's the only place on the HR diagram where we can get full 4 Stokes parameter observations in individual spectral lines at very high quality, because, well, the stars are very suitable for that. They have strong fields and they often rotate slowly, so lines are narrow. So this is perhaps example of I would like to say typical data set, but maybe it's a little bit better than typical. But so it's one of the bright, cool AP stars observed with HARPS polarimeter. And my student, Noam Ruzamarov, has recently published a paper studying this spectra. So what you see here is a rather small interval of just 6 angstrom or so. The entire spectrum actually covers from roughly 4 to 7,000 angstrom. And there are several spectral lines here, and you can clearly see the signal in Stokes V and signal in Q and U. So what we would like to do is to interpret such spectra. And the first studies that tried to recover magnetic field topologies of these stars from observations in all 4 Stokes parameters. I did it in actually first such studies in my PhD thesis 10 years ago. It was a little bit surprising, because even for stars which showed no evidence of deviations from dipolar fields from simple magnetic observables, it turned out that inclusion of Q and U parameters in magnetic inversions do make a difference. We suddenly start to getting much more complex field. And these plots illustrate an example of that. So this is one of the, again, very bright magnetic AP star, Alpha 2 Canon Veneticorum. And the top panel shows the inversion results for the full 4 Stokes parameter inversion when we're using QUV. And this is the distribution of field strength, distribution of field orientation. And then this should be compared with the bottom panel, which shows inversion from exactly the same data set, except that I ignored Q and U. So you can see that with Q and U, the field is more complex. However, the vector distribution of the field doesn't change. It is still kind of bipolar field. So the first approximation is dipole, but dipole with these small features, with local kind of spots. So this is the current view of level of field complexity in these stars. Dipole at first approximation, but going deeper, we might see deviations from dipole. And this is example of fits to a more recent data set obtained for the same star. Well, here I'm trying to compare observations with the best fit Zeeman Doppler imaging model, so model including these small scale features, field complexity in blue, and then dipolar fit is shown in red. And again, you can see that, okay, for Stokes V, red is not so bad, maybe. It reproduces more or less observations, but certain rotation phases in U parameter and in Q parameter are not fitted at all with assuming only dipolar field, but they are fitted if we are allowing this complexity of the field on the surface. we have also started, again, for this particular star, we had this early inversion results in false Stokes parameters based on data coming from now decommissioned musical spectropolarimeter, and these data were obtained in these years, 97, 99, and then more recently we reobserved this star with new spectropolarimeters, so taking data during this period, and this is comparison of magnetic maps from different epochs, now in rectangular format, so you see distribution of radial, meridional, and azimuthal field component, and you can see that there is this distortions, complexity, but this does not change over the time scale of 10 years. So the maps actually are more or less the same, and this is further illustrated with taking the difference between the two maps. So even though we see complex features, it seems that these features on the surfaces of AP stars are still stable. They are not evolving as one would expect for dynamo field. And then I'd like to return to the question of interplay between magnetic field and chemical spots. So there is this mechanism of atomic diffusion, which I mentioned in the beginning, the radiation force that pushes chemical elements upwards. It depends on the spectrum. Okay? It depends on how a particular atom absorbs light. And of course, if magnetic field is present, strong magnetic field, it splits spectral lines, so it changes the spectrum. And it also is more difficult for the elements to diffuse, to travel perpendicular to magnetic field lines if these elements are ionized. So this is how a magnetic field is able to introduce anisotropy in the atomic diffusion process. So our understanding how spots form on these stars is magnetic field somehow modulates, alters atomic diffusion process. So it does it differently for different parts of the stellar surface. So somewhere on the surface, elements are accumulating more efficiently. They are trapped maybe by horizontal magnetic field lines. And there we get a chemical spot. To calculate these things theoretically is quite complicated because you have to really evaluate this radiative force by looking at the entire spectrum. You basically have to calculate model atmosphere of the star, including time-dependent diffusion of chemical elements. And there are some studies that try to do that now theoretically. This is typical examples of such studies. In this case, what I'm showing is the vertical distribution of iron predicted by such models, and different curves here correspond to stars with different effective temperature. I think the black one here is like 7,500, and the pink is maybe 10,000 Kelvin, so F star to A star. And you can see how huge the variation of chemistry in the atmospheres of these stars can be. So this is logarithmic scale, and this is roughly between 0 to -2 log tau. That's the typical line formation range. So even within this range, we can get, well, several orders of magnitude change in chemical composition. So this was a study, non-magnetic one, and then if you introduce magnetic field, the same picture becomes some kind of 2D picture. So this picture attempts to show vertical distribution. So the vertical axis is here, it's just number of layers. So this is the top of the atmosphere, corresponding to this part in the previous figure, and this is the bottom of the atmosphere. And in addition, the horizontal axis show you how things change for different orientation of the magnetic field. So this is inclination of the magnetic field relative to vertical axis. So here magnetic field is vertical, here magnetic field is horizontal. So you see that in the beginning, when magnetic field is nearly vertical, it allows the elements to diffuse upwards. So basically, you get exactly the same pictures here: large accumulation deep in the atmosphere, and underabundance in high atmospheric layers. But then, when a magnetic field becomes almost horizontal, we get this second accumulation in the upper atmospheric layers. And I think this gray bar indicates where solar abundance would be on this grayscale. And these are really the very first attempts to calculate magnetic diffusion of chemical elements, and it only reproduces things in a qualitative sense. Yes, we can get spots, but the problem is, from the observational perspective, that this type of reaction of diffusion on magnetic field is almost the same for all elements. So all the elements would show large accumulation on the top of the atmosphere for the horizontal magnetic field. It has very little variation from, say, iron to other elements. But if we try to compare this with observational results, there is a big problem, because in observations, what we see is really a very large diversity in the chemical abundance structures, in the sense that some elements do show clear correlation with magnetic field. Some elements don't show this correlation. So I here collected the typical results of such multi-element Doppler imaging for a star with roughly dipolar field, which has large inclination, large obliquity. So, this is the map of lithium. So darker areas correspond to higher abundance. And you can see that lithium is somehow associated with magnetic poles. So curiously, in these stars, lithium shows this behavior very much concentrated into the spots at magnetic poles. Oxygen shows just the opposite behavior. It concentrates on the in the equatorial region of the star, magnetic equatorial region here, where field lines are horizontal. And some elements, like in this case iron, don't seem to show any clear correlation. And if we look at elements, other elements, heavy elements, there is a big diversity. So some show small spots, others show large spots, and so on. So that is to say, we have basic theoretical mechanism, and that mechanism may be explaining us why these stars have accumulation of elements, but clearly a lot of effects are missing from the theoretical description, effects which are distinguishing different elements. And that can be maybe something to do with the upper boundary condition, which is used in these models, and meaning that the models of atomic diffusion are very sensitive to what is assumed about the stellar wind. And stellar wind in these stars is so weak that it cannot be characterized observationally. And winds in these stars can be chemically differentiated, so the star can lose different elements at different rate. So maybe that's the explanation. Another explanation that is also quite interesting and being considered now is that, these models that I'm showing here are calculated under assumption that there is stationary solution in this problem. So these distributions are obtained assuming that there is a balance between these two forces, between radiative pressure and the gravity. So these are equilibrium models. But nobody said that real stars can achieve this equilibrium. So in fact, there was a more recent paper where they looked at really time-dependent scenario, so calculated this with real time dependence. And it turns out that the situation can be actually cyclic. So the star accumulates elements high in the atmosphere, and then this cloud then somehow changes radiative transfer, blocks, acts as a kind of layer blocking radiation, and then that decreases radiative pressure, and then these elements rain down, and then this whole thing repeats again. And the time scale of this process is quite long. It's hundreds of thousands of years. So we would not expect to see variation when looking at the same star at different epochs. But in principle, this time-dependent behavior can maybe explain diversity between different elements and also diversity between different stars. And okay, before the break, I also would like to mention one thing, that so far I have really emphasized that the incidence of magnetic fields in intermediate mass stars is like 10%, small fraction of the stars are observed to be magnetic. But recently there has been big effort to make more precise measurements of magnetic fields in normal A-type stars to probe the range of the fields below a few hundred Gauss and down to maybe less than Gauss. And it turns out that actually normal stars, normal A stars, may also have magnetic fields. And in particular, there has been a claim of detecting magnetic field for the two brightest A-type stars, Vega and Sirius. And here, the precision that is presumably obtained here is really impressive. So 10 to the minus 5 is actually the full amplitude of this Stokes V signature. So the formal precision of the observations themselves is few times 10 to the minus 6. And okay, this is obtained combining all spectral lines with a multi-line technique. And this is obtained actually sitting with a 2-meter telescope on Sirius for like 10 nights. So this is the type of observation that is needed to get this precision. So magnetic field is, there are papers announcing discovery of magnetic field for Vega and Sirius. In both cases, field is below 1 Gauss. For Vega, they all even reconstructed using Zeeman Doppler imaging a distribution of magnetic field over the stellar surface. And the range here is between 2.5 and minus 3 Gauss, so just a few Gauss even on the surface. And the field is dominated by this negative polarity spot close to the rotation pole, which might make sense because you might know that Vega is a very rapidly rotating A-type star seen pole own. So there is a strong change in the properties of the atmosphere from the equator to the pole. The situation for Sirius is less clear-cut. So the profile, Stokes V profile, which is obtained, looks like this. So it's a bit unusual because it's symmetric, and because it sort of has the net polarization. If you integrate, you get some positive effect, positive polarization, and that's a bit strange because this is known for the Sun, for local regions on the Sun with strong velocity and magnetic gradients. You can suppress one lobe of Stokes V profile and retain only other lobe. And get this net circular polarization. How it can happen for disk-integrated stellar spectrum is not really known. But we have actually obtained our own data set for Sirius, and we got exactly the same profile with a different spectropolarimeter. So this is results with Espadons and Normal, and Harp's pole shows the same profile. And these fields seem to be stable as well. So, of course, it's very difficult to say exactly. So different epochs can have different noise here, but so far there is no evidence of field evolution. So the bottom line is that, yes, 10% of ABF stars are strongly magnetic, but there may be a hidden magnetism at much lower level, below 1 Gauss. Yeah. Yeah, LSD, yes, yes. Well, of course, there could be a little difference in the line list that people use, but it's least squares the convolution. So I suggest that now we make a 10-minute break and then come back 5 past. Okay?